Let's take a look at 126H, where we're to use the limit comparison test, okay, to determine whether the given series converges or diverges. And here is the series we're given. You can see clearly, if I call these the a sub n's, I think everyone can see clearly as n goes to infinity, the limit of the a sub n's is 0. Again, that doesn't tell us anything other than we have a chance to converge, okay? And so we need to do something else, which is to compare it to a series that we do know converges. And how do we do that? You remember, what we're going to do is we're going to take the highest degree up top, highest degree term up top, well, it's just 1, and then the highest degree term in the bottom. Now in the bottom, notice I'm multiplying n times the square root of n squared plus 1. So what my highest degree term down below is going to be, I'm going to take the n, right, for this factor, and the highest degree term for the square root of n squared plus 1 is going to be just the n squared, but notice it's under the square root. So I'm going to pull off the n and the square root of n squared, but the square root of n squared is just n, okay? N times n is n squared. So this is what we're going to compare it to. And basically for large values of n, what we're saying is this a sub n is going to be very, very close to 1 over n squared, because this 1 becomes very, very insignificant in comparison to n squared, you know, as n gets very, very large, like 100, a million, a billion, a trillion, and, you know, so on and so forth, bigger, bigger, bigger. So it's going to dominate. So basically it's just going to look like exactly that, which, as I've shown below, is equal to 1 over n squared. Now this series, 1 over n squared, we know is convergent. It's a convergent p series, right? Go to your table of series tests and you'll see that's the p series. We've proven the p series, and so we can use that fact. They're convergent if p is greater than 1. Okay, so it's convergent. Now, the thing nice about limit comparison as opposed to direct comparison, I don't have to get any inequality to show that these a sub n's are less than or equal to this. I just simply take a look right at the limit of the ratio of the a sub n's to the b sub n. So I'm calling the b sub n the known series. So here is the limit comparison test here. I'm looking at a particular series here, a sub n. Then if I look at the limit of the a sub n's to b sub n's, in either case here, if it's a finite positive limit, right, positive limit, then if the b sub n converges, then the a sub n converges. This first column, if you remember, is the conditions for convergence. Over here, conditions for divergence. If b sub n diverges, then a sub n also diverges. So that's what we're going to use. And let's take a look at that limit. Do we indeed get a positive finite value? Well, a sub n and b sub n. And let's simplify. Dividing by 1 over n squared is the same as multiplying this by n squared. So I got the n squared up top over the n times the square root of n squared plus 1. I'm going to simplify, right? Divide numerator and denominator by n before I do anything. And I'm getting n over the square root of n squared plus 1. Okay, so far so good, I hope. Notice the form of the limit is infinity over infinity. So you might think, well, let me use L'Hopital's rule. But with this radical down here, it gets a little bit crazy looking. I mean, we actually could use L'Hopital's rule, and that would be fine, I think, in this case. But I'm going to multiply, or actually divide numerator and denominator by the highest degree term in the denominator, which is the highest degree term, of course, is n squared, but notice it's under the radical. So just like I did above, the square root of n squared is just equal to n, right? And that's true, by the way, for n being greater than or equal to 1, which is the case because we're talking about a series starting with n equal 1. It's not true if n is a negative number, okay? If n is a negative number, this statement would be untrue, right? We'd have to put the absolute value around n or something different, right? Or put a negative sign in front of over this radical. But for n being positive, this is true. So I'm going to divide both the numerator by n and the denominator by n. Of course, I'm going to rewrite the denominator division by n by the square root of n squared. And then I can bring that into the radical like that. Of course, up top, n divided by n is 1. Then I divide each term by n squared. N squared divided by n squared is 1. 1 divided by n squared gives me 1 divided by n squared. And now I take the limit as n goes to infinity, and clearly this term here is going to go to 0. And so my limit becomes 1, which is greater than 0. And as we said, then by the limit comparison test, the corresponding series that we were looking at originally is also convergent. Okay, so I hope this makes sense. Keep in mind, you could have also used, I think, L'Hopital's rule in finding this limit, but being able to find a limit is important, obviously, using the limit comparison test.